Welcome to Lesson 3.2. In the previous lesson, Lesson 3.1, we learned how to identify stable frames and calculate their degree of indeterminacy. In this lesson, we'll assume that the frames are indeed determinate and learn how to calculate shear and moment diagrams. We'll start by motivating the study of shear moment diagrams from a failure perspective to learn why calculating these diagrams is important. Then we'll review methods to draw shear and moment diagrams for both beams and frame structures. We'll look first at the more direct method where we cut sections and use equilibrium equations directly. And then we'll look at the more intuitive and simpler approach of using the differential relationships between loads, shear, and moment. And in this process, we'll also look at deriving the differential relationships in a more informal setting. Now, bending a beam creates internal moments, which in turn create stress distributions across the cross-section of the material. The relationship between moment and stress distributions is shown here, where we have the equation sigma equal to my over I. Here, m is the internal moment. This is what we'll learn to calculate through shear and moment diagrams. Y is the distance from the neutral axis, and I is the second area moment of inertia. This relationship creates a linear stress distribution in the cross-section of the material, as you can see from the figure. So stress increases linearly with distance from the neutral axis. So the maximum stresses will always be experienced at the edges of the cross-section. And so that's where the material or the beam will tend to fail. Now, the exact mode of failure will depend on two primary factors. The first factor will be the beam cross-section, as this determines both the position of the neutral axis as well as the area moment of inertia. And it will also depend on the material properties, particularly the material's compressive and tensile yield strengths. If the material is weakest in compression or is being loaded excessively on the compressive side, you would get a failure that looks like the case on the left, where the beam either buckles or crushes locally. If the material is weak in tension or loaded excessively on the tension side, then you would get a tension failure on the tension side of the beam, as you see in the right-hand case. So, from a structural analysis and design perspective, you would ideally design your beam such that the maximum stresses on either the compressive or tensile sides are less than the corresponding material compressive and tensile strengths. Now, long beams will tend to be dominated by bending-induced stresses. However, short beams may be dominated by shear-induced stresses. Now, shear occurs when a beam is pushed and pulled in opposite directions, as you see in the figure. We have a reaction providing a positive force, and we have an applied load providing a negative force. This generates an even stress distribution across the face of the cross-section. And so we can calculate the average shear stress, tau average, as simply the internal shear force, S, which we will learn to calculate using shear and moment diagrams, over the cross-sectional area of the beam. Because of the behavior of shear, it will tend to be greatest near the supports of the beam, as you see in the bottom figure. And it will manifest itself as cracks or buckling occurring close to a 45-degree angle at the point of failure. Now, there are no published standard values for shear strength like with tensile and yield strength. Instead, it is common for it to be estimated as 60% of the ultimate tensile strength. So when designing, you ensure that your maximum average shear stresses are less than 0.6 times your ultimate tensile strength. Now we have seen how values of internal moment and internal shear can help us design beams that will fulfill our required capacity for loads. So let's talk about how to calculate them. The first thing we need to do is establish a consistent sign convention. We denote positive shear as a positive force on the left side of the beam and a negative force on the right side of the beam. This creates internal shears like so. So if we slice a beam and look at the left side, a positive shear will be pointing down. If we look at the right side, a positive shear will be pointing up. The opposite case is true for negative shear, so all directions are flipped. And so a left-looking section will have a negative shear pointing up, and a right-looking section will have a negative shear pointing down. Positive bending is bending such that the physical behavior of the beam is to be concave up. In other words, it's a smiley face. That means that the compression is on the top of the beam and the tension is at the bottom. In this case, the internal moment on the left-looking section will be counterclockwise, and on the right-looking section will be clockwise. The total opposite is true for negative bending, so we simply flip the signs. So be sure to memorize this convention carefully, as we will use it throughout the class. Now, generally speaking, we can express the internal shear forces and internal bending moments as functions of the variable x, which describes the horizontal position along the beam. And also in general, these are discontinuous functions. These discontinuities can be generated by a point force or a point moment applied somewhere on the beam. So let's take a look at an example of a point force in the middle of the beam. We'll simply call that distance L/2. Now let's draw a section to the left of that force, and we'll call that section AA. And we'll analyze the left side of that section. Now we'll express the position of that section in general as a distance x from point A. And we'll also assume that we know the reactions at point A and B. Okay, so drawing that section looking left would give us something like this. Notice how I'm sticking to my positive convention of shear down and moment counterclockwise for a left-looking section. Once we have that section drawn, we can draw upon the equilibrium equations to establish the internal shears and moments. So in this case, we'll do sum of forces in the y direction first to establish shear. That gives us the internal shear is equal to AY. And we'll do sum of moments around the rightmost point to determine the internal moment. We'll call this point R. Note that my moment arm is now dependent on the position of the section, so it's equal to x. So now we've established shear and moment for section A. Now let's look what happens if we draw a section to the right side of that force. We'll call that section BB. And we'll calculate the internal moments also looking in the same direction. We'll go through the same procedure, but note that now P comes into the equations. So in the end, our equations for shear and moment end up being different on the right side. So what we do is we express this as a piecewise function and say that certain equations are only valid for certain ranges of x. So for example, the first set of equations is valid for x between 0 and L/2, while the second set of equations is valid between L/2 and L. Note that the point L/2 here remains somewhat ambiguous because it is a point of a discontinuity. Now let's look at a concrete example to see how to apply this method. Here we have a beam subjected to a distributed force, as well as a point force of 5 kilonewtons and a point moment of 20 kilonewtons per meter. Note that the reactions have already been provided to us, but in a general case, we would need to calculate those as well. Now, the first thing we need to do is identify points of discontinuity. This will happen at the point of application of the point force. We'll call this point C, and it will happen at point B as well, where we have the point moment. Therefore, we need at least two sections here to create two piecewise functions that will describe the shear and moment distribution throughout this beam. So we'll draw a section to the left of C, we'll call it AA, and then we'll draw another section to the right of C, and we'll call that BB. Note that I'm always choosing to look left, but you could very easily choose to look right as well to solve this problem. We'll describe the position of these sections by using the variable x. So let's first look at section AA. So in a similar way here, we'll start with some of the forces in the y direction. Note that now, because we have a distributed load, that distributed load gets multiplied by x, the position of our cross section. Therefore, we have, now in order to determine the internal moment, we'll again do the same procedure and calculate moments around the rightmost point. This allows us to take the shear force out of the equation. Note that now we have three moments in this equation. One obviously is the internal moment. The next is the moment due to the reaction. And the last is the moment due to the distributed load, which would be equal to the total force from that distributed load times its moment arm, which will act directly in the center of the distributed load. Once we have those numbers, we can simplify to 6x minus x squared over 2 kilonewton meters. And of course, this is only valid from point A to point C, and so we must make a note of that. Now let's take a look at section BB. So now we've included the 5 kilonewton force in the equation, and again, same procedure. So we get the shear force equal to 1 minus x, and again we do sum of moments around point R, and in this case this simplifies to note that these equations are valid for x between point C and point B, or in a range between 4 and 10 meters. Note that to be precise, I should strictly keep this in terms of less than signs. And so I should go back here and also change that as well, as the reactions are also point loads and thus discontinuity. So we can only express x on either side of a discontinuity, but not specifically at a discontinuity. So make a note of that. Only use greater than or less than signs. Now this method is great for understanding where the shear and moment diagram distributions come from, but it can get tedious for more complex structures. However, if you're sharp, you'll realize that the shear distribution, S, is simply the derivative of the moment distribution, M, and this is true in all cases. So let's derive that a little more formally. Here we have a general beam with a distributed load, point forces, as well as point moments. But first, let's consider a small portion of the beam where no force or moment is applied. We'll call that portion delta x. And we'll imagine that this portion is very, very small. So if it's very, very small, then the distributed load across that portion will be effectively constant. So we can treat it as a uniform distributed load, W. We'll also have shear and moments on either side of the element, and we'll assume that there's a slight change delta S in shear and a slight change delta M in moment. So once we have those forces established, we can do a equilibrium calculation for this element and start with the sum of forces in the y direction. Notice how the distributed load W simply gets multiplied by the delta X to give us the total applied force on that element. And simplifying this, we see that the S's cancel out. That leaves us with things in terms of delta S and delta X. So we get W is equal to delta S over delta X. In words, this would be that the intensity of the distribution is equal to the slope of the shear. Then we do the sum of the moments around the leftmost point. We'll call this L. Now looking at this equation, we can substitute delta S based on our previous equation. Now, here's the tricky bit. Since we are dealing with very small values of delta X, we can assume that delta X squared is much, much smaller and essentially round it off to 0. That means we can get rid of this component as well as this component because it gets multiplied by delta X. In addition, we can get rid of the M's since they cancel out. That leaves us with S equal to delta M over delta X. In other words, the shear is equal to the slope of the moment. And there you have the fundamental relationship between distributed load, shear, and moment. If we differentiate the moment, we get S, shear. If we differentiate the shear, we get W, the distributed load. In the other direction, we would simply integrate. We can also use the same approach to look at the effects of concentrated moments and forces, which, as we will see, cause jumps in the shear and moment diagrams. Now, in order to do this, we'll look at two different elements, one with a point force applied and one with a point of moment. But in order to keep our convention straight, we will make a slight change to this diagram and make our forces and moments positive. So we will have our force point up and we will have our moment act counterclockwise. This will be our positive convention for externally applied loads. Once we do that, everything else stays the same. So let's do sum of forces in the left element to get the change in shear. As you can see, this simplifies rather easily to delta S equal to F. So a positive force will cause a jump up in the diagram. Now let's look at sum of moments in the second element, and we'll do that sum of moments around point O. As we can see, this causes a slightly different result. We get delta M equal to negative M bar, and therefore a positive moment counterclockwise causes a jump down in the moment diagram. Now let's look how to apply these concepts to the same example we did before. We start by drawing a set of horizontal lines below the beam. One will represent the S diagram and one will represent the M diagram. Then we'll start with the S diagram, and we start from the left side of point A and we'll work our way through the beam all the way to point B. Now we know that on the left side of A, the shear must be 0, but as we move to the right, immediately we encounter the 6 kilonewton reaction force. That results in a jump up of 6 kilonewtons. Then we have to deal with the distributed load. Now remember that the slope of the shear diagram is equal to the distributed load W, which is 1 kilonewton per meter. Okay, since that is pointing down, it is negative, so our slope is going to be negative. So our shear diagram is going to slope down with a slope of -1. Notice that because the distributed load is uniform, I know that slope is linear. Over the range of 4 meters, that slope is going to lead to a decrease of 4 kilonewtons, so the value at the discontinuity right before C will be 2 kilonewtons. Then at C, we have the downward applied force of 5 kilonewtons that causes a negative jump of 5, so that gets us to 3 kilonewtons, negative 3, and then the slope continues to slope down at a slope of negative 1. So over the range of 6, that decreases by an additional 6, so we get negative 9 at this point, and then we have the positive 9 kilonewton reaction that jumps us back to 0. Okay, that is a good sign. That means that our structure is in equilibrium, because obviously to the right of B we should expect 0 shear force. So that is our complete shear diagram. Now we move into the moment diagram. Now we know that the shear represents the slope of the moment diagram. So that means that the moment diagram is going to have a quadratic shape, since the shear has a linear shape. And because our shear is decreasing over time, that means that the slope of our moment diagram will be decreasing over time. So it will have a quadratic shape in this way. So we know that the moment at A is 0 because there is no moment at that support. But we must calculate what the moment is at C. To do that, we know that the change in moment from A to C is simply corresponding to the area under the shear diagram. The area under the rectangle is equal to 8, and the area under the triangle is also equal to 8. So the total area is 16. That means the change in area from A to C is 16. 0 plus 16 gives us 16 at this point. Then we'll go ahead and calculate the area of the shear diagram on the right side of C. That gives us negative 18 for the rectangle and negative 18 for the triangle, for a total area of negative 36. That means that our moment right before B will be negative 20. That is simply the difference between 16 and 36. And then all we need to do is roughly estimate the shape of the curve between these two. And because the shear now becomes more negative as we go from left to right, then so should the slope of the moment diagram. So it starts with a slightly negative slope and continues down. And finally, we just must account for the point moment of 20 kilonewtons there at B. Note that because of the convention we established, a clockwise moment produces a positive jump, and so we end up at 0 here, right to the right side of B. Again, that lets us know that we did this correctly, because there should be no moment to the right side of B. And there you have it. That's how you draw a complete shear and moment diagram, including point loads as well as distributed loads. Your challenge before the next class is to draw the shear and moment diagrams for this frame. In order to do so, it's easiest to split it into two separate diagrams, one vertical and one horizontal. So in order to do that, you'll need to find the internal loads at the intersections, but then from that point on, you can treat them as reactions for the purposes of drawing the moment in shear diagrams. So give it a shot, and we'll cover this in the next lecture.